These journals contain stunning images of the construction of the Titanic and its near-identical twin, the Olympic. I found these journals at the University of Illinois Library. The journals, written between 1909 and 1911, take me back to a time before the Titanic sunk. They give me a new perspective and let me appreciate the enormity of the scale of the engineering of the Olympic-class ships. So, let me share with you some fascinating details about the Titanic and its twins, the Olympic and Britannic. The story starts here in the Harland and Wolff shipyard in Belfast, Ireland. This large framework, called a gantry, surrounds the ships as they are built. It supports the overhead cranes and scaffolding used by workers as they construct the Olympic and the Titanic. Notice that just beyond the far end of the gantry lies the Belfast harbor. Workers will build the Olympic here on the right, and then 9 months later, before the Olympic is finished, they will start on the left the Titanic. When completed, the Olympic stern, or rear end of the ship, will point toward the harbor. The ship's construction starts with its keel, seen here as a long, dark shape. The keel is the backbone of the ship and gives the ship rigidity. If we look at the keel from the land side, we see the keel blocks that support it. These wooden blocks, typically pine, separate the ship from the slip, the concrete floor of the gantry. Each keel block stands about 5 feet high, so this creates a space under the ship for workers to construct the ship. Workers build the ship outward from the keel. Here they construct the Olympic's double bottom. In pink, we see the framework that separates and supports the two bottoms of the ship. The second bottom is shown in orange. It's made of steel plates and is sometimes called the tank top because the double bottom contains 44 watertight tanks. Most of the tanks carried seawater used as ballast to balance and add weight to the ship, but some carried fresh water. In total, the double bottom carried over 5,000 tons of water, or about 1.5 million gallons. Once they finish the double bottom, workers erect the framing for the hull. From this view, we see the framing for the stern of the ship. It's what a worker would see standing on the tank top from the fore and looking toward the aft of the ship. That's where the harbor is. Looking closer, we see the rib-like structure on the start of the transverse frame of the ship. Workers rivet to this frame the hull, which will form the skin. So far, we've watched the Olympic's construction. In the gantry, that ship sits here in the background. In the foreground lies the keel of its twin, the Titanic. Its construction began 9 months after the Olympic. We see here, attached to the keel, the framework of the Titanic's double bottom. Notice this large, claw-like mechanism lying on the ground, and these three hung from the cranes. These are hydraulic riveters, which workers used to install most of the 3 million rivets on the Titanic. Here we see the almost complete hulls of both the Olympic and Titanic. Work inside the Olympic progresses rapidly. The staterooms are being erected, and plumbing is being fitted throughout the ship. To prepare for the Olympic's launch, workers paint the ship a light gray so it will stand out in black and white photographs, although they repainted the ship black soon after its launch so that it matched previous White Star liners. To ease the slide into the water, the slip was greased with 23 tons of tallow, oil, and soap. And then the order to release the ship was given, the hydraulic triggers were released, and the ship slid into the harbor, reaching a speed of 12.5 knots. Notice that the ship is launched backwards. There are many reasons for this, but among them is that the stern, the rear, is wider than the bow, so it is more buoyant. In a mere 62 seconds after launch, the Olympic was afloat. The moment the ship hit the water is its official launch date, although it was mostly empty. Here it weighs only about 27,000 tons and so rides high in the water. The draft, the vertical distance between the bottom of the ship and the surface of the water, is only 18 feet. After it is completely fitted, it will weigh nearly twice that, 52,000 tons. With that additional weight, the Olympic will drop until the water reaches the border painted on the hull, a draft of about 34 feet. The Olympic cannot move by itself, and so a tugboat tows it to the fitting out quay where a gigantic crane loads the ship. Here the crane lifts aboard a cylindrical boiler. The final fitting, including attaching the propellers, is done in dry dock. And then, once everything is in place, the Olympic is ready for the sea. 7 months after this launch, the Titanic was launched. I have from this journal a few photos of that event, but keep in mind the Olympic got the big press because it was first. The Titanic only becomes of more interest in retrospect. This photograph shows the twins, the Olympic and Titanic. Although built side by side, this was the last time they were photographed together. Less than a year after the launch of these two giant ships, one suffered a collision that ripped a gaping hole in its side. That ship was, of course, the Olympic. In September of 1911, the Olympic departed the port of Southampton, England, sailing toward the Isle of Wight. The Olympic turned into the Solent Strait and passed a British warship, the HMS Hawke. The Hawke's commander was surprised by the Olympic's wide turn, but he managed to take a safe position behind and to the right of the Olympic. The Hawke then increased its speed to pass the Olympic, but the Olympic's wake sucked the Hawke inward rapidly. The Hawke tore a large hole in the Olympic, and below its waterline, the damage was even greater. The bow of the Hawke was completely smashed in. The Olympic limped back to Southampton, where the holes were temporarily patched with wood before returning to its home dock in Belfast for repairs. The Olympic's sibling also suffered a traumatic blow that caused it to tragically sink. I'm of course talking about the Britannic. The Britannic was the same size and very similar to the Olympic and Titanic. Although intended to be a passenger liner, the ship was drafted into military service in World War I as a hospital ship. While in the Mediterranean, it hit a mine or was struck by a torpedo and sank in less than an hour. Despite these accidents, the Olympic-class ships were great feats of design and workmanship. Just consider the propulsion system of the Titanic. The ship had two sets of reciprocating engines. These engines were fueled by coal, which was stored along the bottom of the ship. Exhaust gases from the boiler discharged through these smokestacks, which are frequently called funnels. Now, they don't look like funnels until you look at them the right way. They're upside-down funnels. This cross-section of the Olympic shows the boilers sitting atop the double bottom. Exhaust from the boilers is funneled up and out of the ship. It's well known that the aftmost funnel on these ships is a dummy. It was built primarily for aesthetic reasons. Although it did not service the boilers, it was used as a ventilation and extraction shaft for the engine and turbine rooms. The Titanic needed 4,000 tons of coal for a transatlantic trip, which took 24 hours to shovel into the bunkers. Here, in this photo of the SS Minnehaha, coal is being loaded into coal ports on the side of the hull. Loading coal into the Titanic worked much the same way. This loading left streaks of coal dust on the hull, and so nearly all ocean liners at the time were painted black to help hide these traces of coal. After the advent of oil-fueled ships, lighter colors became more popular. As the Titanic crossed the Atlantic, 650 tons of coal per day was shoveled into cylindrical boilers where it was burned to produce steam. These boilers were nearly 16 feet in diameter. This picture shows a single boiler. Notice the two workers beside it. The steam was piped to these reciprocating engines. The engines, when viewed from the front of the ship, look like this. The orange is the piston rod, and inside the cylindrical casing is the piston. This worker peering out of this casing gives a sense of the engine's size. Excess steam from these engines was used to drive a turbine engine. This shows the turbine under construction and without its outer casing. Note the workers at the top. This is huge. If you look closely, you can see that the turbine is made of hundreds of individual blades. A shaft transfers power from the engines to the propellers. The ones on the left and the right were powered by the reciprocating engines, and each propeller weighed 38 tons, while the central propeller was powered by the turbine engine. It was cast as a single piece of manganese bronze and weighed 22 tons. The outer propellers were used for tight navigation of harbors, while the central propeller was used only in open seas. Also, unlike the others, the central propeller could not be driven in reverse, only forward. Even with this powerful propulsion system, the Olympic-class ships were not the fastest at the time, which was intentional. The White Star Line decided to focus on comfort and luxury over speed. It's clear that the lavishly decorated rooms on the Olympic and Titanic certainly made the passage more enjoyable, but there were some hidden design choices that made these ships the pinnacle of comfort for all classes of service. The ships were steered using these helical gears. Each ship had two sets of both the spur gears and the beveled gears. These massive gears are nearly 6 feet across, made of solid steel, and each weigh thousands of pounds. Notice the herringbone pattern on the teeth. This pattern allowed a tight engagement of the teeth and resulted in reduced vibration transmitted to the rest of the ship. Altogether, the gearing on the Titanic weighed about 7.5 tons. This very large structural piece is called the boss arms. These arms held the shafts of the outer propellers in place, and because of their size and strength, they reinforce the hull, which reduces panting. Panting occurs when variations in water pressure, say the crest versus the trough of the wave, flex the hull inward and outward. Less flexing results in less vibration felt by the passengers. These boss arms, also called shaft brackets, were fitted 20 feet apart at the very aft of the ship. While the Titanic and Britannic both had tragically short careers, the Olympic triumphed. In its lifetime, it made over 500 transatlantic journeys, carrying over 400,000 passengers and sailing 1.5 million miles. It even spent 4 years as a U.S.-Canadian troop transport during World War I, earning the nickname Old Reliable. After 24 years of service, the ship was decommissioned and scrapped for parts. The Olympic-class ships were absolute marvels of engineering. I hope it's for their revolutionary design rather than their failures that they're remembered. I'm Bill Hammack, the Engineer Guy. I thank my advanced viewers for their useful feedback on a draft of this video. If you'd like to be an advanced viewer, sign up at engineerguy.com/support. Thanks for watching.